In our last lecture, we showed how we can use u-substitution to prove the formula for integrating functions with linear composition that we made a solid justification of in section 1.1. And in fact, u-substitution can be used to answer a few other lingering questions from the first section of the course as well. When we were putting together our list of common integrals, we observed that we were able to use our knowledge of differentiation to get integrals for sine and cosine, but not to get integrals for tangent or cotangent or secant or cosecant. The best we could do was to come up with integrals which resulted in those functions. But with u-substitution, now we can go a little bit further. So first of all, let's talk about tangent and cotangent. We're going to show that the integral of tangent is given by negative the natural log of the absolute value of cosine x plus c. And very similarly, the integral of cotangent, that's the positive natural log of the absolute value of sine x plus c. And that might seem a little bit surprising. Why would natural logarithms suddenly pop up when they didn't in the integrals for sine or cosine? But we can justify this using u-substitution. We won't prove both of these because the derivation is essentially the same in both cases. Let's concentrate on the first one. Let's get the integral for tangent. And the way we do this, the way we can make u-substitution apply here, is by remembering that tangent is sine over cosine. So, of course, that means that the integral that we're interested in here, the integral of tan x, is the integral of sine over cosine. Now, in section 1.1, that would have been a bad thing. It's a quotient. And at first glance, even here, it might seem, well, it's a quotient. It doesn't have any composition in it. Is u-substitution necessarily going to apply? But one of the things that we've seen a few times now is that we don't always need composite functions present to use u-substitution. Sometimes, as with our rational functions, we can find some other expression whose derivative, maybe lacking a constant multiple, is also there in our integrand, and that can suffice in order to use u-substitution. And of course, cosine and sine, they're each other's derivatives. Now, would we let u be sine so that du could be cosine x dx? Well, no, that's not going to work because cosine is in the denominator here. We don't have a cosine dx, we've got a 1 over cosine dx. But we could certainly do it the other way around. So let's let u be cosine x. Then du is negative sine x dx. But that negative is fine, because just like any other constant, we can just divide it across to the left-hand side. Dividing by -1 or multiplying by -1 are the same thing. So that tells us that negative du is sine x dx. So then, we can rewrite the integral. So our integral for tan x is now going to be, let's see, we're going to have the integral of the cosine is our u, and the sine x dx is going to be negative du. So that's really, because of course the negative being a constant we can bring outside. That's negative the integral of 1 over u. Again, we keep seeing this one, and it does pop up pretty often. So, of course, that's then going to be negative the natural log of the absolute value of u plus c. And then we just plug back in for u, as always, to obtain our result. we could do the exact same thing to get the integral for cotangent. In that case, we'd write cotangent as cosine over sine, let u be sine x, and then cosine x dx would be the du. And that's why, in that case, there's no negative in front of that logarithm, because of the fact that when we differentiate sine, we do get cosine, whereas here, when we differentiate cosine, we do get that extra factor of -1 that we have to handle. So there we go. There's two more common integrals that now just really get added to our list, the list of 14 or whatever it was that we derived in section 1.1. We can tack these on as well. And these are integrals that are just worth knowing by heart because they come up often enough. But in the worst case scenario, if you do forget them, now you know how to derive them. Something else that's worth noting is that this one here, the integral for tangent, you'll sometimes see it in a slightly different form. So instead of writing it as I've given you here in the theorem, we could use our properties of logarithms. And remember, any constant in front of a logarithm can be brought inside as a power. So we can instead write the integral of tangent as the natural log of the absolute value of cosine x to the power of -1 plus c, which is the natural log of the absolute value of 1 over cosine. And remember, the reciprocal of cosine is secant. So we could also write the integral of tangent as the positive logarithm of the absolute value of secant x plus c. And some textbooks will cite that as the primary result. It really doesn't matter which one you use. Technically, we could do the same thing for the integral of cotangent, but then we'd actually have to introduce a factor of -1 in order to bring a -1 inside and take the reciprocal. So while it is true to say that the integral of cotan x is negative the natural log of the absolute value of cosecant x plus c, why introduce an extra factor of -1 in front and have the more obscure, the secondary trigonometric function inside the logarithm? There just doesn't seem to be a particularly good reason why we would ever want to do that. So we can leave the negative for tangent, we can leave the negative in front and have the more common function, the cosine, inside the logarithm, or we can get rid of the -1 and have the secondary function, the secant, inside the logarithm. Doesn't really matter which one, but for cotangent, we always leave it as the natural log of the absolute value of sine x. And so now we can just use this like we can any other common integration result. So for example, if I wanted to integrate, let's say, the tangent of x over 5. Well, that's another one of those integrals with linear composition. So the same pattern that we've already observed, that's going to apply here as well. We've just said that if this was just the integral of tan x, then we get negative the natural log of the absolute value of cosine x plus c. So in this case, we're just going to replace the x with x over 5, but we also have to divide by the coefficient of the x. So that means we're going to get negative the natural log of the absolute value of cosine of x over 5 divided by the coefficient. So divided by 1/5 plus c. And of course, we'll want to simplify that. Dividing by 1/5 is the same as multiplying by 5. So we can write this as -5 times the natural log of the absolute value of the cosine of x over 5 plus c. Or, again, if you prefer the secant expression, you can write it as +5 times the natural log of the absolute value of secant of x over 5 plus c. And that's a perfectly reasonable way to write that one as well. So there we go. We've got our results now for the integrals of tangent and cotangent. Well, we already had sine and cosine, so we don't want to leave secant and cosecant out in the cold. Let's do those in the next video.